Hello, everybody, and welcome. Hello, everybody, and welcome to the fall seminar series. Today, we are privileged to have Dr. Michael Dorneich, who is an assistant professor at Iowa State University, presenting to us. Before joining the faculty at Iowa State University, Dr. Dorneich worked at Honeywell Labs, researching adaptive system design and human factors in a variety of domains. He was also a visiting scientist at NASA Ames Research Lab. His research interests focus on creating joint adaptive human-machine systems that enable people to be effective in the complex and often stressful environments in aviation, military, robotic, and space applications. His recent work looks at the development of adaptive stress training systems, cognitive assistance for space operations, and the development of human autonomy team frameworks. Dr. Dorneich has authored over 200 publications and holds 28, very impressive, 28 US and international patents. Dr. Dorneich, we are most grateful to have you. The floor is yours. Thank you.
Well, thank you, Dr. Newman. I appreciate the introduction, and I appreciate the chance to present today. So I guess with that, we'll just go ahead. And, I would say if people have questions, feel free to interject or maybe type them in chat, and then I can try and answer them at the end of the presentation. So first, let me ask, is everybody seeing my title slide?
Yes, I can see that.
Okay, great. Okay, so I'm going to talk about a project that we just finished up with NASA, and where we're looking at adaptive training system to inoculate astronauts for stress using a virtual reality environment. So first of all, as I mentioned, the project was funded by NASA, and our program manager was Kelly Reed. And we actually had several faculty and graduate students or students on the project. So my background is human factors and adaptive systems, as Dr. Newman was mentioning. Warren Franke was our expert in physiology. Nir Karen was our expert in virtual reality, and Steve Vardaman was our expert in statistics. And then Tor Finseth was the graduate student who did all the heavy lifting on this project. And this was actually part of his dissertation work, and I'm glad to say that he successfully graduated in May. We also had a small army of undergraduate research assistants. So they helped us with things like data collection, running the experiments, some data cleaning and analysis as well. And so I want to recognize their contributions. So what I'm going to talk about today is the project and give an introduction and some motivation. And then I'll talk about the overall approach about how you develop these kinds of systems. And then some key aspects of the system. So identifying the stressors for training, developing the training logic and how we would adapt, how we implemented the system in virtual reality. And then I'll briefly go through 3 experiments that really covered some of the components and then putting the whole system together. So it's probably no surprise that space operations require highly skilled performance in a harsh operational environment. And it can be very stressful due to the hazards and off-nominal situations, and that stress may jeopardize the performance and mission success. So there's lots of different kinds of spaceflight hazards. I'm not going to go through all these, but they require some sort of response from the crew, usually under highly stressful situations. And crews get a lot of training, and they may have trained for some of these, but that training doesn't happen very often. There might be a long time between when they got the training and when they did it. And that training really focused on task performance. But it doesn't really focus on how to handle the stress that comes along with these kind of situations. And we know that stress can impact performance. So if we look at the definition of stress, so here's one where stress is defined as a transactional situation between the individual and the environment, where the individual's perceived demands tax or exceed the perceived resources. So if you look at that definition, there's an appraisal phase. Basically, you're presented with a situation and you ask yourself, do I have the resources to handle that situation? And then the degree to which that answer is no, that can cause an increase in stress. So not every stressor is created equal, and something that stressed you out today may not stress you out tomorrow if you have more resources to handle things. Now, there's a lot of different outcomes of stress. So there's emotional reactions, there's cognitive effects, physiological changes that are associated with stress, as well as social effects. So we're most interested in those cognitive effects. So some of those effects might be things like narrowed attention or reduced performance or impaired decision-making. The physiological changes, on the other hand, are things that we might be able to actually detect, so that if we want to detect that someone is under stress, we might look at things like their heart rate, their blood pressure, other physiological markers of that stress. So despite high levels of skill training, stress can really sabotage that skilled performance, and especially associated with emergencies where there's a degree of uncertainty, or perhaps that situation hasn't been encountered very often. And so these are all things that can impact performance. So historically, NASA does training, and it relies heavily on things like task rehearsal, so that astronauts practice over and over again to do their to be able to handle a certain situation. But again, these situations could happen long after they were trained. And historically, NASA looks at a couple different ways of mitigating risk. So you might have specially trained crew members that are assigned to specific tasks or mission critical tasks. And then any kind of procedures, especially emergency procedures, are closely monitored and supported by the flight controllers on the ground. They have a much broader access and a deeper pool of information and expertise to help the crew deal with situations. So that works well in low Earth orbit operations like the ISS, but it's not a viable way to manage these kind of situations in deep space operations where there's a communications delay. You certainly can't move personnel very quickly. And so that leads to the need to train for more situations. So when we think of training, there's different kinds of training. And so skill training we're all familiar with, where you acquire the knowledge about how to do it, the task. You rehearse different procedures. Those procedures are fairly straightforward, or at least set down in a straightforward way. But what we don't have as much of is stress training. So there is stress training out there, but usually it's in more of a therapeutic setting. Usually after exposure to a traumatic event, it's really about recovering and developing coping mechanisms to develop ways to handle stress. So we're interested in supplementing skill training with stress training. And so part of what we're trying to do is figure out exactly how to do that. So there is stress training out there. So stress inoculation training, for instance, is a type of cognitive behavioral theory that is about developing coping skills so that when you're in a stressful situation, you know how to cope them. And those are fairly generalizable skills. And then stress exposure training, where you're applying these coping mechanisms while you're doing the tasks, and you're exposed to stressors as you're doing those tasks. Typically, there's three phases. There's an education phase, a skill acquisition rehearsal phase, and then you apply the coping skills that you've learned. So if we want to think of the system and the people within it as something that we want to be resilient, so resilience is the goal, really there are three ways to try and address that. So if we look at this chart, this is kind of the classic stress versus performance. Some stress is good, it actually improves your performance, but too much can degrade your performance. So there are different things that we can do. So for instance, we can use this exposure training to first maybe lower the levels of stress overall, so that should promote better performance. Or perhaps we can try and train so that your performance is higher, even under stressful situations, or that we maintain some optimal level of performance at higher levels of stress. So this led us to this project that we proposed to NASA, and we had several aims. So first, we needed to identify the components and principles that contribute to stress in the environments that NASA cares about. What kind of methods can we use to measure and adapt for stress? And then can we develop a prototype, in our case using virtual reality, that evaluates people's stress and then uses rules and triggers and other state assessments in combination to decide, do we need to make any changes to the training? And so then our goal was to conduct a proof of concept of the training and evaluate whether this is a viable approach. And eventually we'd like to establish guidelines for the implementation of this kind of training. So if we're successful, then we can optimize the exposure to stressors during training so that hopefully we help build up those coping skills. And this should lead to an improved response when you're actually doing the task in real life and you have novel stressors or novel tasks. If we can do this in a virtual reality kind of environment, that would be a training system that might require less resources, both in money and personnel. Often you have to have a trainer that optimizes your training. If we can do that automatically, that would be a huge savings. And so the goal here is that this kind of training could be used in deep space operations. So if we look at all that translates to some research tasks. So as I mentioned, our objective is to implement this adaptive stress training for hazardous conditions with the goal of reducing that stress response and enhancing performance. So we'd like to apply some of these graduated stress exposure, which again are usually for therapeutic reasons. Now we want to apply them to healthy subjects to maintain performance under stress. And the goal here is to gradually increase the stressor levels during training. And then not only that, but we'd like to optimize or customize or maybe even personalize that level of stress to your current state. What's your current stress level? Where are you in the training? And so can we personalize that training? So this translates to some research tasks. So first we need to figure out just what are the stressors in this environment that will help us, you know. So what tasks will we train and how do we manipulate stress during that training? Tasks 2 and 3 really develop the components and then put everything together in a closed loop training system. And then finally, we want to run some experiments where we first want to test some of the components and then put everything together and see if the system works. So that first task, we put a panel together. We had a retired astronaut, a flight director, as well as some experts in physiological and psychological stress. And we presented various different kinds of emergency procedures and layouts of the ISS. And the goal here was to figure out what are the stressors that could happen. And now I'm not expecting anybody to read this chart, but what the take-home message here is that really there were two categories of stressors. One was we can change things in the environment so that the environment can cause you stress, or we could change things in the task. We could make the task harder, and that would cause you more stress. And what we realized pretty quickly is that we wanted to focus, on the environmental stressors, because we didn't want to mix. If we start messing with the task to create stress, well, we're also messing with the task while we're trying to train the task. And so we didn't want to confound task difficulty with the training and the stress manipulations. So we focused on thinking up environmental stressors that we could add to the situation. And then this is a modified form of the fire response procedure for the ISS. And so this is what we ended up using in our project. So now that we have a way to manipulate stress in the virtual environment, we want to think about some of the other components. So this is an overview here of the closed loop architecture. We start with, I don't know if you can see my cursor here, but we start with the person and we hook them up with things like heart rate monitors, blood pressure, galvanic skin response. And from that, using some machine learning techniques, we want to develop a real-time measure of stress. If we have that, we can then have a training module that says, well, we have a pedagogy that says, you know, halfway through the training, you should be at about medium, halfway through or further in, you might be able to handle higher levels of stress. So that's our pedagogy of that graduated stress exposure. And then the adaptations manager basically makes the decision of, if I look at your current stress and I look what the training module says your stress should be, do I need to make any changes? And those changes then happen in this virtual reality environment. So let's first look at the training module and the adaptations manager. So, so a little bit about vocabulary here. So I'm trying to be very careful when I use the word stressor versus the word stress. So stressor is something that causes stress. So I might, more noise, more lights, things in the environment are stressors, and they should cause more stress. So if we start here, let's say we're 60 seconds into to a trial here. The blue line actually says what is the stressor level in the virtual environment set to right now. The red line here says what is our real-time measure of stress. So we see for this person there was some transient sort of medium stress, but then it kind of settles down to a low level. So at 60 seconds, we ask ourselves, should we change anything in the environment? So first of all, what's the target level? And so this dotted line says, well, our pedagogy says that we should be having the person at about a medium stress level. And so we make the decision here that, well, they're at a low stress level. We actually want them higher. So let's move our actual stress level up to a medium thing. So we do that, and then we get some more data, and now 60 seconds go by, and we're faced with the decision again. Do we adjust the stressor levels? We see that we want them at medium, it's set at medium, but their stress level is a little bit higher than that, so probably we won't do anything for the next 60 seconds. So to do that, we have some rules. So we basically want to say, is that stress level, the current stress level of the participant, at the target stress level that we want? And if it's not, then it's time to make a change, either lower or raise that stress level. But we have some constraints here, and this is a large part of this work was trying to figure out what these constraints were. So first of all, we wanted to be pretty positive that we have a good measure of that real-time stress. If we get that measure wrong, then the system is going to be bouncing around all over the place and not really reflective of what the current state of the human is. So I'll talk a little bit about the classifier we developed. We developed it so that we could see the conditional probabilities, and we wanted a minimum 70% conditional probability. So think of that as our confidence that the stress prediction is probably true. You'll notice in the slide before that we only adapted after 60 seconds. So there's always this transient when you make a change, your body reacts, but then you kind of settle down into whatever level of stress you're at. We're not going to make a change unless we're at the same stress level over 2 consecutive windows. Again, we do that so that we're not jumping around too quickly. We're kind of dampening the response. And we have these target levels. So you'll see later in our experimental design, we have trials. We start with low, and then we do a couple of trials of medium, and then a couple of trials of high. And so that's the maximum that we would allow in any trial, depending on which trial it is. And again, in a sense, to be a little bit conservative, so that we didn't jump around too much, we can increase stressors, but we can't decrease. So now we have our rules, and we have our training pedagogy. So the next thing we want to think about is that virtual environment. And if you remember, the whole goal of the virtual environment is that we want to manipulate your stress levels. So we want to be able to see whether we can do that. So we started with a virtual environment of the International Space Station, but NASA was actually interested in something a little bit closer to the Gateway, the Lunar Gateway Station. That's a smaller station. And so we closed off some of the modules and just worked in these 3. And their job of the participants was to locate and extinguish a potential fire. And so you do this by taking contaminant readings. It's not like you can just see fire. What you really see is just smoke, because often this fire is within walls or something like that. And you read contaminant readings, and basically you take a reading here, you take a reading a little bit farther away, you compare them, you decide which direction that tells you to go. But of course, the readings you took 5 minutes ago are now a bit old and out of date. And so this is actually a very cognitively demanding task. But then when you do find the fire, we tell you to extinguish it. So we designed this virtual reality space station, and we developed it with 3 different stressor levels. And again, as I mentioned before, we wanted to just use environmental stressors. So So the three levers that we had that we could adjust were the level of smoke that the fire was producing, the alarms, how loud and distracting were those alarms, and then the lights themselves, were they on, were they flickering, things like these. So these are the things that we can manipulate to try and create these different levels of stress. In our virtual environment, we had things like an oxygen mask, a fire extinguisher, control panels or alarm panels, and then this handheld contaminant reading device that you could bring up and see. Now, I hope this will work. The next slide is a video. Usually takes a few clicks here to get this thing to work. There we go. We'll give that a second. So what we see here is that they put on the oxygen mask. That actually, they were very concerned about running out of oxygen, even though we gave them sort of unlimited oxygen. Here you see they get their extinguisher. They can actually put it on their belt because this is a zero-G environment. So they actually need to use their hands to push off in the environment. And then you can see there's the contaminant reading device. They don't see this out the window view here. That's just to give you an idea of what it looked like. But you can see the compartment is starting to fill with smoke. They need to move around. There's some obstacles. They're taking these readings, trying to locate that fire. So it gets stressful pretty quickly. All right, so let's continue. Okay, so now we have an environment that we can manipulate the stress, and you've got a sort of a flavor of that. The last component here was that measurement of stress. So how do we take things like blood pressure, galvanic skin response, heart rate, and turn that into your level of stress right now is medium. And so we used machine learning for that. And then we actually developed our own machine learning process. We call it approximate Bayes, and I don't really have time to go into that. We're about to submit a paper on this, in fact. But what it gave us were not just like in a traditional classification algorithm, you have a bunch of data, it extracts some features, and then at the end it tells you, is this a cat or is it not a cat? So it's binary, 100% or 0%. We actually wanted some level of confidence of the classifiers or these conditional probabilities. So here, the classifier is saying, well, it's a 60% chance it's low stress, but there are some non-zero chance that it's the other levels. And so this is what we used, if you remember back to those rules, to only trigger changes in our virtual environment when we had a very strong indication of one of these levels. Again, I'm not going to go into a lot of details here, but basically we had these 4 sensors. We added respiration at some point. You can extract a bunch of features. And then what we actually did was then decide which features are relevant for this person, because some people may have a reaction with blood pressure, some may have a reaction with a different physiological marker. And so we needed to personalize this for each person. So we select some features and then we classify using ours, A-Bayes, as well as some other methods. But if you think about how we're using this, we're actually using this in real time. So we want to train our classifier to that individual, but then after that, we're just running open loop. And so we really needed to create a system for that real-time streaming of that data, and then that very quick classification so that we can have that measure in a timely manner. So again, sorry, I don't have enough time to go into details with that, but that system now gives us that real-time measure of stress. So now we've talked about each of the components. Now let's talk about evaluating these. And you know, it's kind of a maxim when you put these kind of systems together that you really need to study each of the components in isolation before you put everything together, because there's a lot of different ways that this system may not work. So for instance, if we were never actually able to manipulate your stress, then all the conditions were the same and we have no levers to make any meaningful changes. Or it could be that we had good stress manipulations, but we triggered them at the wrong time because our gauge didn't tell us the right level of stress. And so we're sort of misapplying good mitigations, or we have bad mitigations that we're applying at the right time, but they're not effective. So we need to test each one of these in isolation. So our first one was to test this manipulation. Could we manipulate stress in a virtual environment? You know, there's plenty of examples, even from my career, where it's a little bit hard to stress people out in a virtual reality, but then if you're running around with soldiers and people are shooting soap bullets at you, it's very easy to stress them out. So our goal here was to establish that we could manipulate those levels of stress. So we ran an experiment with 62 participants, where we basically put them in that low, medium, and high stressor environments. And so these are our definitions. Again, we could play with the smoke and the alarms and the lights. And so in low, there were no stressors, but in high, there was heavy smoke, there were continuous alarms, there were flashing lights. And so that we hoped would be a much more, have much higher stressors than the low. And so we basically put them in these three, and then asked a lot of different kinds of subjective responses. And what we found was that when we asked them right after each trial, what was their stress level, and then looked across the three trials, we do indeed see significantly different levels of stress. We also asked them at the end of the experiment to look back at the three levels and assess their levels of stress. And once again, that post-appraisal also came up with very distinct levels of stress. What we see with workload is that the high stressor level did have slightly more workload than the other two, which weren't significantly different from each other. And that's kind of an indication of what I was saying before, that playing with the stress levels does impact the task difficulty in some sense. So they're not completely clean, but we're at least trying to separate those as much as possible. As far as distress and mood there, we didn't see as much differences. And so what this experiment provided us was justification and evidence that we were able to manipulate stress the way that we wanted. So now we have a virtual environment that allows us to put you in a low stressor environment, a medium stressor environment, and a high stressor environment. So the next thing to validate was that real-time measure of stress. So we can manipulate stress. Well, can we measure it? And so that led to study 2. And so we had this newly developed A-Bayes classifier, and we wanted to compare that to other classifiers to see, are we in the same ballpark? And again, we developed this because we wanted those conditional probabilities, and that they were easier to get with this new approach. Now, let's take a moment to review how we're going to use this gauge. We're going to train it low, medium, high, and then we're going to deploy the system and run it on unseen data through these trials during training. So the question is, how do you validate a system like that? So traditional machine learning validates things through cross-validation, where you have one data set and you pull out some of that data for training and some for testing, and then you see how accurate it is, and then you sort of divvy up the data in a different way, and you do this over and over again, depending on how much of the data you're using for training and testing. And so you're creating these separate partitions, or they're called folds, with equal amounts of data points, and then you test the training against the test data. Well, that's not how we're going to use our gauge. So a different way to validate this is something called holdout, where we pull out the last part of the data, and we don't use that at all to train the system ever. We just use the earlier part to train the system, and then we test it on the holdout so that it's truly unseen data. And so we'll test this in both ways. So for this experiment, we had 41 participants, and we gave them actually 2 tasks. We gave them that emergency spaceflight task that you've seen already. We also gave them a laboratory-based task, the NBAC task, which is been shown over the years to be very solid in the kinds of reactions that it gets from people. And so we know exactly what we would expect with that. And so that's a little bit less complex, more direct than this VR task that we're doing. So the NBAC, for those that don't know, basically you're given a stimulus here, you're given a square in one of these 9 positions, and you're asked, is that in the same position as it was one stimulus ago? That would be a 1-back. So that's pretty easy. If you basically see a repeat, you say, hey, yes, otherwise you say no. But a 2-back says, well, is the current stimulus the same as it was 2 stimuli ago? So now you have to keep two things in working memory and sort of update that as you go. So that's harder. So you can imagine 4 back is about as much as people can handle. And then, so that's our laboratory task, and then our virtual environment task we've seen before. And again, I'm going to jump right to the results. So we see about an 87% accuracy at predicting stress for those 3 classes. So a lot of classifiers are 2 classes, these are 3. And we see good agreement across the different folds. So 10-fold is when you use 90% of the data to train and 10% to test. 2-fold is it's more 50-50. And then that holdout, where we hold out some data that we never use to train and test on that, we're seeing very similar results. And so basically what this is telling us is that the model, the A-Bayes approach is pretty robust, and we're seeing similar results in all these different validation methods, as well as the window sizes. So I'm not going to go into detail there, but you can think of the window size as how much data do I need before I make a determination. Do I need 10 seconds of data? And then I say, okay, based on those 10 seconds, you're at high, or 20 seconds, or 30, or 40. And so again, we see a pretty robust response across all these different time windows. So what that tells us now is that we are able to classify those 3 levels of stress, and gives us confidence that we're classifying on unseen data, so that we can basically trust our gauge to tell us what the stress level is. And this is a key component to personalizing the training, because this classifier is personalized to the person. Remember that we're determining which are the features that are most relevant for that person when we train the system, so that when we're using it, we're picking up a good, strong signal. And so now we have this personalized stress detection approach. And so that allows us to test all kinds of different people. And that, again, this A-Bayes gives us these approximations of these conditional probabilities, which are important for those rules that I mentioned earlier. Okay, so finally, we're going to put all this together. So we're going to look at this whole system all together and see what kind of effect this graduated stress exposure training might have. So to give you an example of how people might differ, and this is all notional data here, but in this first trial, remember the black line is the target stress level the training module is saying we should be at. The blue line is sort of the setting of the virtual environment, and then the red line is the actual real-time stress result. So we see here that the stress is pretty high, even though the VR is set at low. And so in the second trial, VR is still set at low. We could move up to medium, but the red line is so high that we don't dare move up to medium. They're already stressed out more than we want them to be stressed out. But we see in trial 3 that they're starting to approach medium, and which is where we want them. And then it even gets lower, so that here towards the end, we're getting a low stress response, but we'd like it to be medium. So now is the time to move up, to push that stressor level up, which is what we see in the 4th trial. And we never really go to the high until the last trial. So this is a slower inoculator. It took longer than those fixed black lines to get there, to get the environment up to those levels of stressors. In contrast here, for a fast inoculator, you can see that in that first trial, their stress goes down pretty quickly. So that allows us in the second trial to raise that stressor level, that blue line, up to the target. And then in the third one, we can see that even though we're at medium, their stress level is low. So as soon as we can, after that first 60 seconds, we raise it up to high. And so you see that they've reached that high stressor level in the environment sooner than the previous example. So our experiment looked like this, where we had 3 different groups. So you were randomly assigned one of these 3 groups. So in the control group, you didn't get any stressor training whatsoever. It was always low. The environment never changed. You basically came in, you did a high sort of baseline, and then you did 4 trials of practice under low, and then you had another high stressor level. In group 2, we do use graduated stressor levels, but we use those fixed levels. We don't actually personalize between the different people. It's just, you know, the system is going to change when it's going to change, and it doesn't matter whether you're ready for it or not. And then group 3 is this adaptive system where it's graduated and adaptive. So now we will adapt what level of stress you are in that environment depending on your real-time measure. And what this allows us to do is to test, you know, are groups 2 and 3 better than group 1? That would tell us that graduated stress exposure has some benefit. And then is group 3 better than group 2? You know, it might, you know, if we don't need to go through all this real-time measurement of stress, that we can just use fixed levels and it works for everyone, that would be great. But, you know, do we need to adapt? So in this experiment, we had 65 participants. We had a better gender split. We were really looking for more of an astronaut-like population. And so NASA defines that as a 50-50 gender split, ages between 25 and 49, or 55 actually, and that everybody has a background in STEM. And so you can see from our statistics, we were trying to get close to that. And again, I mentioned these 3 experimental groups. We had a bit of an uneven number, but fairly close, at least 20 in each. Our dependent variables, we had a lot of physiological measures as well as some subjective scales to test their stress response as well as their task performance. And I don't have time to go through all these, but I'll show a summary slide. The first thing we wanted to ask ourselves is, did that adaptive system even trigger? You know, maybe those rules never fired, and so things just operated the same as the middle condition. But as you can see in the adaptive condition down here, we did have variation between people, and sort of the average stress level was different. So that's good. So that our rules are triggering. And this is actual data where you can see that people were very different as far as what when the system actually made changes to the stress level. So here's a summary of the results. So the dark blue are when P was less than 0.05, P less than 0.1 is more sort of marginal or trending in the right direction. And really this first 3 columns is the thing to look at. Think of this as a preponderance of the evidence. We have a lot of different physiological measures, both physiological and subjective. And we see in the skill only that, you know, even just practicing the task should help you lower some of your stress, at least the stress that's associated with the task. And sure enough, we see a few of the measures here start to go in the direction that we would expect. And the numbers in parentheses is the effect size in units of standard deviation. With the graduated, remember that's the fixed levels, we start to see more of these measures show us that there is some beneficial effect on stress inoculation. And then finally in the adaptive, we see most of these measures now are telling us that, that there is a positive response as far as inoculating stress. You can also do a more classic ANOVA. That actually has some problems just because of the way the data is structured. So those results are less clear, but these straight t-tests here show us what we're looking for. So again, we want to make sure that our manipulation worked. And so we looked at the stress levels through the 3 training trials, that low, medium, high. We know what that should be. And sure enough, we see different stress levels. So our manipulation continues to work. So here's an example result. And the thing to look at really are the slopes of these lines. Because ideally, like we see in this task engagement here on the left, you should all start out at exactly the same spot, because in trial 3, you haven't done any of the training yet. And so there's no difference between these subjects. And in this graph we do, but in other ones, you'll see that there's some difference. So really pay attention to the slope. And so what we see here is the adaptive has the slope in the direction we want. So the blue arrows tell you which direction is higher stress. So in this case, going a higher number means that you're lowering your stress. And so we see that adaptive lowers the stress, where graduated actually increased the stress, and skill only was no difference. What we see for anxiety is that everything is in the right direction, but not much difference in the slopes here between the different results or the different groups. As far as some of the physiological measures, so for heart rate, we do see a stronger slope for the adaptive. That's the red dashed line in both heart rate and the LF versus HF. That's a frequency response. And so what we're seeing is, like we saw in the numbers, it's reflected in these graphs, that the adaptive condition seems to have a stronger response than the graduated or the skill only. So if we put all that together now, all three experimental conditions showed that we had an increase in some of the physiological measures, RMSD, P, and N50. These are based all on heart rates. They're some of the standard measures of stress. And so we had an increased vagal control. So if you think of our reaction, we actually have two systems. Think of one as the gas. We're under stressful, so we ramp up. And we have another, which is the brake, which is that vagal control, which is more about our ability to recover or relax after a stressful event. And so we're seeing that people are able to recover and dampen their stress response with this adaptive training. And so our conclusion here is that this adaptive system can reduce stress over multiple training systems, and furthermore can do it better than just the graduated or the skill only. And this whole system was built in a way that all this is happening automatically. There's not a trainer sitting there watching you and then making changes to the environment. This is a typical way to train people, is to have a trainer sort of with you in real time doing it the whole time. All this is automatic, and so it requires less trainer support. So finally, in summary, stress can be manipulated using a virtual environment. So that's what study 1 showed us. We can detect it with that A-Bayes approach and that personalized approach to stress detection in 3 levels. And so we showed that with study 2, and that we can accurately predict stress with that new A-Bayes procedure. And then that finally study 3 showed us that adaptive system can reduce stress over multiple training sessions. So the idea of graduated stress exposure has some merit as far as having some beneficial effect over stress. And so, and finally that this is all happening in an automated system, fairly lightweight, in a virtual reality environment. So this is just kind of the tip of the iceberg. If you think about future work, some individuals may inoculate differently. We didn't really train them on any kind of coping strategies, so we could think about doing that and investigating, are there different kinds of coping strategies? There's a lot of refinement in the training pedagogy. How long should these sessions be? How much time should there be between sessions? That really speaks to the retention of some of the benefits that you get out of the system. We didn't, that was out of scope in our project, but that would be an important thing to study. And then we're always looking for better measures of things like stress inoculation and even task performance. The stress detection itself. So, can we classify stress? Can we train that stressor on you and use that the next day, or do we have to retrain? That's always a question with classification. Are there other pre-processing things that we can do to clean up the data so that we end up with better classification? And one of the things about this data is that it's all time series data, so it's not independent observations of the same thing. And so the fact that we're dealing with physiological signals really should change the way we try to measure them. And then finally, for the adaptive system itself, there's a lot of testing we can do. We never tested decreasing stressor levels. Are we overwhelming some of our people by going too fast? And then working on different rules. And so I think I've hit about time. So I'm happy to take questions, and thank you for your attention.
Yeah, thank you, Dr. Dorneich. Thought that was a very, very great and insightful presentation. So at this point, if you have a question, you can chime in and ask your question, or alternatively, you could use a chat to ask your questions. So the floor is now open to the audience to ask questions.
I have a question.
Okay, yeah.
Hi, I'm Dr. Drowitz, also human factors. So have you thought about how this may work from a teaming perspective? You did it with individuals, but a lot of these emergency situations, you're going to have a team of people. So how does a team or, interactions within that team and impact these stressors and this adaptive prediction?
First of all, let me say absolutely. I think that's one of the logical next steps. And in fact, that's a huge research area of mine. I'm really interested in human autonomy teaming, so both humans working together and working with automation. And you can kind of think of this as an automated agent because it's making its own decisions as far as how to do that training. So I would love to extend this work to multiple humans working together. And one of the interesting things about the minute you move to teams, everything in the training right now was about task skills, but there are also team skills. So I might be very good at my task, you might be very good at your task, but if I'm a terrible communicator, that's going to impact how we work together as a team. And so training those kind of skills is actually some of the work we do in other projects. And again, it's the same kind of challenges. How do you measure those teaming skills? How do you manipulate those situations that require people to use those skills? And so we're actually trying to develop a virtual environment test bed that requires people to come in and do a task. It's kind of a game that would elicit some of these teaming skills so that we have a test bed to test some of these things. And then layering training on top of that would be pretty exciting, I think.
Thank you. I have another question, if that's okay.
Sure.
Why did you choose virtual reality and not augmented reality? Like build a actual physical environment and have augmented reality kind of put the stressors augmented to the physical system. Just wondering the approach of why virtual.
Yeah, and in a way, I think you almost answered your own question. In a virtual reality, we have the ability and also the responsibility to design all of it, right? Where in augmented reality, you get for free whatever you're using in the environment. You may have to build it, but you can leverage it with your virtual content. So we were trying to focus on something that we thought would be deployable in a closed kind of environment, up in space and things like that. So we pretty quickly decided virtual reality. But thinking about it a little more deeply, I think it was the ability to control all aspects of the environment that also made it attractive. Where augmented reality, some of that environment is outside the system, which you can leverage, but then you don't have that level of control.
Yeah, that makes sense. Ideally, I guess you'd have a zero gravity chamber and then augmented reality, but that would cost a lot of money.
Well, and a lot of pilot training is remarkably constrained because they got to fly people to some training facility,
right? Yeah.
Other places, and so I think the last I heard, or I heard this once, so don't quote me on this, but that the average, the astronauts train about 2 years for a mission, and they get about 32 hours on emergency procedures. Wow. In those 2 years. Wow. So they're training for a lot of different things.
Thank you.
Sure, thank you.
Any more questions? So whilst we wait, I have a couple of questions I would ask myself.
Great.
So great work. I thought you came across very well, especially given that most of the research in this space is offline processing of the data, and you took it to the next level of online processing. So my question is, what are the competing resources required to do this? Yeah,
so I would say the biggest drain on resources, computing resources, would be that real-time classification. And so we employed things like parallelism and tried to optimize as much as we could of that processing. But other things that we had to think about were things like, how much data do we classify at once? So is it 10 seconds versus 40 seconds? And there's some interaction with physiology, right? Our heart rate is about 1 to 2 hertz, right? But if you're using something like EEG, which we didn't, that could be 2000 hertz, right? As far as signals that you're getting and things like that. So part of the sensors that we deployed It's realistic to think about real-time processing of heart rate. There is some real-time processing of EEG, but that's some pretty heavy lifting there. And so a lot of this was, a lot of our decisions about where to, at least our starting decisions, had to do with that vision of, okay, this is something that someone can put a headset on and train, while sitting in a space station or something like that, right? We haven't at all thought about, how are these physiological sensors affected by microgravity? That's another research project, probably not our research project, but there are plenty of problems to solve as well.
Yeah. So that leads me to my next question of your design of the A-base classifier.
Mm-hmm.
So would have been interesting to see how the traditional classifiers compare in terms of accuracy to yours, one, and then two, your choice of the holdout versus the cross-validation, and how the traditional approach is also compared to yours.
Yeah, actually, the paper we're looking to submit has all that, right? So we compared it to support vector machine, random forest. I forget what the third one was. Somewhere I actually have a backup slide on that. But all the results came out about the same, in that 87 to 90% range. In the paper, we actually dig a little deeper into those window sizes. And it turns out that 30 seconds is about the optimal window size. Again, if you think about heart rate, it's not changing on a 10-second basis. It's changing more on a 30 to 60-second basis. Yeah. So that seemed to give us the best. And what we found was that for pick one of those window sizes. There's lots of different measures of the goodness of classification. So specificity, accuracy, other measures. And, that the A-base was kind of right around the middle, so sometimes support vector might have better accuracy, but less specificity, where A-base might be the opposite or something like that. And so everything, I would say that probably all four of the approaches we took, including A-base, were all within maybe 10% of each other on any one of these measures, and usually smaller than that, right? But they're usually, so in some cases, A-base was the best, some cases support vector machine was the best, but what we were really looking for, are they about equal? Are they, are we in the ballpark? Because we're testing our sort of very first attempt at A-base against these packages that have all been optimized for these.
Yeah.
So we were pretty pleased with the results.
Okay. Yeah. So again, I don't know if there's any other person has a question, but I will continue with my other question. My next question, which obviously is you have so many HRV features. I mean, my last count was around 15. If you look at it from the time domain, frequency domain, and the geometric domain. So in your choice of the thing, I saw PNN50 and then RMSD. Why? So question is, why did you decide on those ones? Was it that you threw, because I have my graduate student working on something similar, but I've asked him to pick all these features and do some kind of feature elimination to see which classifier gives them the best. So I don't know how you guys arrived at these three to know that those ones are the best.
Yeah, that's a really good question, and you actually touched on something where there's a bit of a story behind it, right? So we started with defining exactly what features we thought were the most important based on literature, to say, hey, these are the features that the classifier should use. And our results were, okay, but the more we investigated and looked at what people were doing, even outside of physiological, at some point we realized, we shouldn't be a priori saying which features we're going to use. Because if you think about it, you can generate all kinds of features, the mean response, the average, the median response, the standard deviation, the slope over a time period. And one of the things that we thought that actually drove this whole conversation was the fact that our data is not independent data. It's not like we have a picture of 100 cats and it doesn't matter what order we do it in. We're actually, this is time-based data. And so we wanted some features that capture that time-based data. So we actually switched to doing feature extraction. or feature selection and feature extraction. So we took those 4 sensors and those measures and then generated literally hundreds of features. So for every one of them, it could be mean, median, slope, just on and on, right? And then we used a feature selection process where we said, okay, for this training data, for this person, these are the features that are sort of significant, that show a significant difference. And we're going to just classify on those features. So we would down select from 400 to 15 or something like that. But that 15 was different for different people. And so we did see some commonalities, some came out more. Blood pressure seemed to be a very good measure for a lot of people. But there were some people where, the blood pressure features weren't the ones that rose to the top. And so we started with, hey, we know what's important. And we ended with, okay, we'll let the data tell us what's important.
Okay. Yeah, I mean, I look forward to the paper you're talking about. Because it's something I'm very much interested in here.
Yeah, I would love to talk more about it, actually, because this is a fairly new area for us. So.
Yeah, sure. I'll contact you as far as that's concerned. Yeah. Okay. I don't want it to be between the communication just between me and you. So let's see if anyone has. Okay, so someone just sent a message in the chat.
Yeah, so you're talking about that extended U model of stress, and that there's this comfort zone that exists between seeing a negative impact on adaptability with hypo or hyper stress. So what can be said about our participants' ability to adapt to the task at hand? Yeah, and so part of what we were doing with the stress detection was that, again, we would let the data tell us how well they're adapting to the stressor levels. And so as far as their adaptation to the task, we did have task performance measures that we were taking simultaneously. I wouldn't say that they were the greatest measures of task. We could look at how many fires they found, but the whole task was finding a fire. So we would look at things like average distance to the fire and things like that. So I don't know that we had really good measures of how well they were adapting to the task. Our focus was more on their stress response. And there again, we were trying to keep them in that comfort zone or that optimal zone, given where we wanted them, right? So the training pedagogy, those black dashed lines and the figures that I showed were really important to say that our training pedagogy says that at the beginning, you shouldn't be too stressed. It's actually a negative training if we stress you out too much. We might overwhelm you and that might hurt training. Where in the middle, we want to give you medium. And then at the end, we want to kind of throw the kitchen sink at you and see how well you do. And so kind of combining that graduated stress procedure, if you will, or pedagogy with their real-time measures was our attempt to keep them in that comfort zone or that optimal training zone. Hopefully that answered your question.
Yeah, okay, he says it did. Yeah, okay.
Excellent, thank you.
Yeah. So, yeah, so still have some 2 minutes. I guess I could ask my next question. So, I mean, you did look at, I didn't see anything on EDA, electrodermal activity. Did you collect data on that and was that used?
Yes, we did. So I can't remember if we used GSR or EDA, but actually I think it was EDA now that I'm thinking about it. But anyway, we did have some sort of stress response, looking at sweat on the finger as one of our sort of core sensors. For a few people, that was important. Those features rose to the top, but a lot of them it didn't, and that surprised us a little bit. That's usually a pretty reliable indicator of stress. It could just be that in comparison to some of the other measures, it wasn't as diagnostic. But we did take it, and for some people, it was the sensor that produced the features that were important for that person.
Oh, okay. And my last question will be how you can extend this work in other domains like firefighters and other work domains?
Yeah, you know, I think it has broad applicability in different kinds of tasks, different kind. In fact, Nir Karen, one of the faculty on this, has a long history of working with firefighters in virtual environments.
Oh, okay.
And so that's an obvious area. I have some colleagues who work with law enforcement, so I think those kind of things. You know, virtual reality is good for any kind of training that you want to do that maybe it's either logistically difficult, too expensive, too dangerous to train. And it's in those hazardous conditions where that stress response matters a lot. And so I think, you know, take that as your recipe and then start looking for applications that fit that, right?
Yep.
So.
Okay. Well, I think it's a very good time to draw the curtain on this seminar. We are most grateful, Dr. Dorneich, for having taken time off your busy schedule to be with us and to present this very insightful talk. Again, to all participants, this audience, this has been recorded, so you can always revisit it. And if you have any question, you can send Dr. Dorneich an email, or you can send an email. I'll forward it to him.
Absolutely.
So I wish you guys a very good rest of your day, and thank you very much again.
Thank you all. I appreciate the opportunity. Take care.
Okay.
Thank you.